This is a walkthrough of a simple Newton's second law problem, just to sort of solidify the steps that you would follow. So let's say that we have flat ground. That's supposed to look flat. And we have a thing like that. The wheels just show that there's no friction between the ground and the mass. And let's say that the mass, is 20 kilograms. And we have a force this way of 30 newtons and a force this way of 20 newtons and a force down of 50 newtons. And we want to know what's the acceleration vector of the cart. Well, we're going to use Newton's second law. Anytime you're going to be relating forces to accelerations, you're going to use Newton's second law. So before you do that, you always have to draw a free body diagram. So we're going to start by drawing a free body diagram of this mass. Pause the video and draw the free body diagram. Okay, so you have an outline of the body. You always apply the weight force. So that's 20 times 9.81, that's 196.2 newtons. And then you have, well, let's first put in the three forces that are given. We're not told what's applying these forces, they're just given. So we have 20 newtons that way, 30 newtons that way, and 50 newtons that way. And the last thing that we have to do now is just go around the boundary looking for contact. So where do the surroundings make contact with the boundary? The only place is at the wheels. I'm going to lump, even though it's happening at both of those two locations, we're always just going to lump it into one spot because, remember, we're treating these bodies as particles that don't have, so everything really happens at one point right now. Okay, so the contact is here, let's say. And so now you have to think, excuse me, you have to think about whether that's a pushing, a pulling, or a friction contact, and then apply the force based on that. So pause the video and see if you can do that. Okay, that's a pushing contact. So that force is perpendicular to the surface, perpendicular to the ground, toward the chosen body, and we don't know the magnitude of it. I'll give it the name N. Okay, now we have to put these into Newton's second law. So Newton's second law says, so each one of these we have to represent as a force vector. The 50 is in the negative y direction, so that's 0, negative 50. The 20 is in the positive x direction, so that's 20, 0. The 30 is in the negative x direction, so that's negative 30, 0. The weight force is in the negative y direction, so that's 0, negative 196.2. The normal force is in the positive y direction, so that's 0, positive n. And all that is equal to the mass of the body, 20 kilograms, times the acceleration vector. Okay, so now you have to think, does this thing move along the x or y axis? And the acceleration vector is only going to have a component in the direction, in the x or y direction based on that. So pause the video and see if you can come up with the way to represent this acceleration vector. Okay, this thing only moves along the x direction. It turns out, maybe you can tell since the 30 is bigger than the 20, the acceleration is going to be in the negative x. But we don't even have to think about that. All we have to do is figure out x versus y. So this motion is along the x-axis, and so I'm going to write this as a0. And I'm not worrying about whether that's a positive or negative. That'll come out in the math. Now we have two equations. The first one, so the x equation, says 0 plus 20 minus 30 plus 0 plus 0 is equal to 20a. And so that says negative 10 is equal to 20a. Divide both sides by 20, and you get that a is equal to negative 0.5. Okay, that's an answer for a, but that's not a vector yet. So in order to make that a vector, notice that, we've already represented the acceleration vector. It's this in the dotted line. So all you have to do is substitute a in there. So pause the video and give the final acceleration vector direction, final acceleration vector. Okay, so the answer, if you substitute the variable a into that vector, is negative 0.50. Or another way you could represent it is, since that's in the negative x direction, that's a vector in that direction, the negative x, with a magnitude of 0.5 meters per second squared. And either one of those two is a fine way to represent the acceleration vector.